Hi, this is Dharani Murali and you are watching part 1 of ACE Math series. In that, today we are going to start class 10 NCERT chapter 1 real numbers. So what real numbers are? Any number which can be represented on the number line can be called as a real number. Real number comprises of two types of numbers which are rational and irrational. Coming to the rational number part, we can say a number which can be expressed in the form of a by b, where the denominator or the b is not equal to 0. Or in other words, we can also say that a number which can be expressed as the ratio of two integers is called as a rational number. This rational number consists of three major type of numbers, which are integers, natural numbers and whole numbers. Coming to the integers is comprised of negative, 0 and positive numbers. Natural number comprises of positive numbers and whole number comprises of 0 and positive numbers. So this is what is all about rational numbers. Now coming to the irrational part, we can say it is exactly opposite to that of the rational numbers. That is, it cannot be expressed in the form of the ratio of two integers. It cannot be expressed as ratio of two integers. Now, what irrational numbers are comprised of? We can say that it comprises of root values of non-perfect square numbers. So, if we take root over perfect square numbers, what will happen? Let's take an example. Root 25. 25 can be prime factorized as 5 into 5. So, root over 5 into 5 will give the answer as 5, which is a integer. An integer cannot belong to irrational number, so root over perfect square numbers cannot be irrational. We can also say that irrational number comprises of non-terminating and non-repeating decimal expansions. The most common example is pi value, which we use in the formula of the mensuration parts, that is surface area and volume formula. We generally use this pi. Pi can be expressed as 22 by 7. Though simply we represent pi as 3.14, but still pi value is non-terminating and non-repeating value, so it comes under irrational. This is what is all about the introduction about real numbers. Now we will get into the actual chapter, in which the first topic we are going to see is fundamental theorem of arithmetic. The fundamental theorem of arithmetic states that every composite number can be expressed as product of primes, and this factorization is unique except for the order in which the prime factors occur. So, we say that every composite number can be expressed as the product of primes. We will perform the prime factorization method in the conventional way. For example, if we take 6, we can prime factorize it as 2 into 3 and 3 into 1. So, the 6 composite number can be expressed as 2 into 3. So, this is the first part. Every composite number can be expressed as product of primes. We have expressed 6 as 2 into 3, where 2 and 3 are prime factors of 6. Now coming to the second part. This factorization is unique. Unique means the number of prime factors occurring in a particular composite number is always unique. If there is 1, 2 and 1, 3 in the prime factorization of 6, then it is unique. There is no other combination of prime factors which can represent the composite number 6. And it is also said that except except for the order in which the prime factors occur. That is, we can either write 6 as 2 into 3, or we can also write 6 as 3 into 2. Whether it is 2 into 3 or 3 into 2, number of times a prime number occurring in the factorization is unique, but changing the order does not affect the value of the composite number. So this is what is given in the fundamental theorem of arithmetic. This method can also be said as prime factorization method. We generally used to find HCF and LCM using this prime factorization method. We'll see elaborately like how to find LCM and HCF when we solve the exercise now. Now coming to the condition, for any two numbers A and B, this condition is valid. That is, HCF of the numbers and the LCM of the numbers, when their product is taken, then it will be equal to the product of the original numbers. That is, HCF of A comma B into LCM of A comma B will be equal to the product of the original numbers. So this is what is all about fundamental theorem of arithmetic and the relation between HCF and LCM of the numbers. Now let's start with the exercise 1, which is related to this topic, and this information is for those students who are using the previous edition, in which the exercise we are going to start now is second exercise 1.2, because in the new edition Euclid's division lemma, the first part of the chapter is removed. Now we are starting exercise 1 of this chapter. The first question says, express each number as product of its prime factors. So exactly we are going to use the fundamental theorem of arithmetic in this question. First subdivision, the number given is 140. We are going to prime factorize this and express this number as product of its prime factors. While prime factorization, we generally consider the single digit primes as the first preference. Now for 2, we can say any even number is divisible by 2. So if the number given is a even number, or we can also say that every 0 ending number is divisible by 2 as well as 5. So first, since 2 is lesser than 5, we will consider the smaller number first. So we take 2, divide 140 by 2, we get 70. 2 into 70, 140. Now again 70 is a 0 ending number, we can divide it by 2. So taking 2 here, we will get 2 into 35, 70. Now the number here is ending with 5. Any number ending with 5 and 0 digits will be divisible by 5. So we are taking the factor 5 here. For 35 we get 5 into 7. Now 7 itself is a prime number. So either we can stop here or we can conclude it by 7 into 1. Generally we stop it at 1 so that we need not proceed further. These are all the prime factors of 140. So we write 140 equal to 2 into 2 into 5 into 7. But this is not the simplest form to represent any prime factorization. So we generally club the same and repeating prime factors, and we represent it in the form of exponents. Since there are two numbers here, we take it as 2 power 2 into 5 into 7. This is the final solution for this problem. Now coming to the second subdivision, the number given is 156. This is an even number. So first we will take 2, divide 156 by 2, we get 78. 2 into 78, 156. Now again 78 is an even number. So again we will divide it by 2 and we get 39. Seeing this, it is ending with 9. Now we will consider all the single digit prime numbers. It is not an even number, so it cannot be divided by 2. It does not end with 5 or 0, so we cannot consider 5. The other prime factors remaining are 3 and 7. Now taking 7, we know that 39 does not come in the 7 table. 7 fours are 28, 7 fives are 35 and 7 6 are 42. So 39 does not occur in 7. Now we take 3. When we take 3 and we divide 39 by 3, we get 13, and 13 itself is a prime number. So 13 into 1, 13. Now 2, 2, 3 and 13 are the prime factors of 156. So we write it as 156 equal to 2 into 2 into 3 into 13, and we write it in the simple form, that is 2 power 2 into 3 into 13. Now coming to the third subdivision, the number given is 3825. It is a 5 ending number, so obviously it will be divisible by 5. So we use 5 and we divide 3825 by 5. We get 765. Again this is a 5 ending number, so we divide it by 5 and we get 153. Now 153 is divisible by 3. So we take 3 into 51, which is 153, and again 51 is divisible by 3. So 3 into 17 would be 51. 17 itself is a prime. So obviously this is the last step of this prime factorization. 17 into 1, 17. Now we can represent 3825 as 3 into 3 into 5 into 5 into 17. Now this is not the simplest form, so we combine all the same and repeating prime factors and we put it in the exponential form. So 3 power 2 into 5 power 2 into 17 will be the final solution. One more thing can also be noticed here, that in these two questions we have followed the exact order of the prime factorization in the solution also. But here we have changed the order. Here first we have taken 2 5s, then 2 3s and 17. But here we have first taken the 2 3s and 5s and 17. Generally we represent the prime factorization in increasing order. So we start with the smallest number coming in the prime factorization. So that is why we have changed the order and written 3 into 3 into 5 into 5 into 17. Now in the fourth subdivision, the number given is 5005. It is a 5 ending number. So we will directly divide it by 5. We get 1001. Now when it comes to the 1 ending number, we can take it as either we can try it with 3 ending primes, 7 ending primes, like 3 into 7 gives 21. So we try it with 7, we get 143. 143 is divisible by 11, so 11 into 13 gives 143. 13 is a prime number, so 13 into 1 is 13. Now we represent the primes in the ascending order. Here no more simplification is required as none of the prime factors are repeated here. Now coming to the fifth subdivision, the number given is 7429. We divide it by 17 and we get 437, and 437 is divisible by 19. So we get 19 into 23, 437, and 23 is a prime number itself. So we conclude it by 23 into 1, 23. Here also none of the prime factors are repeated. So we directly write 7429 equal to 17 into 19 into 23. Now we are moving on to second question, which is given as find HCF and LCM of the numbers, and also verify LCM into HCF is equal to product of the numbers. This is what we saw in the theory part, that HCF into LCM is equal to the product of the numbers. Now we have to verify this condition for all the subdivisions of the second question. Now the first question, the numbers given are 26 and 91. Now we are going to prime factorize these. 26, it is an even number, so we will divide it by 2 and we get 13. 13 itself is a prime. So 26 has primes 2 and 13. Now coming to 91, it is a one ending number. So basically we will check with 3 and 7 divisibility. Now it goes with 7. So 7 into 13 would be 91 and 13 is a prime number. So 91 has prime factors 7 into 13 and 26 has 2 into 13. Now we have to find the HCF of these two numbers. For HCF, what we will do is we will check which factors are all common in both the factorization. So 26 has 13, 91 also has 13. So whichever number is common in both the numbers, we will take it for HCF. Here only one number is common. If any other number is also common between the two, we will take that also as a product here. But since 13 is the only prime common for both these numbers, we take HCF is equal to 13. Now coming to the LCM, whichever number is common, we will take it only once, and all other prime numbers, we will take it in the product. So LCM will be 2 into 7 into 13 and we get 182. This is the first part of the problem, finding HCF and LCM. Now let's move on to the second part, that is verification of the condition. First let's find the left hand side part of the condition, HCF of 26, 91 and LCM of 26, 91. We are taking the product, we get 13, that is HCF, and 182, that is LCM. So we get 2366. Now let's find the right hand side of the condition, that is product of numbers, that is 26 into 91, which we get 2366. And here we can see that both these values are same. Now let's put it in the proper order, that is HCF of 26, 31 into LCM of 26, 31 equal to 2366, which is equal to 26 into 91, that is product of the numbers. So the required condition is verified. Now coming to the second subdivision, the numbers given are 510 and 92. So first step, we will prime factorize them. In 510 we get, it's an even number, so 2 into 255, it's a 5 ending number. 5 into 51, which is 255, and 51 is divisible by 3, so 3 into 17 would be 51. 510 is equal to 2 into 3 into 5 into 17. Now coming to 92, it is an even number, so we will divide it by 2. We will get 46. Again, while dividing by 2, we get 23, and 23 is a prime number. So we get 92 is equal to 2 into 2 into 23. Till this, we have completed the prime factorization part. Now, for finding HCF, we will see how many prime factors are common in both these numbers. So here if we see, first number, this 2 is common. So 1, 2 we will take for HCF, and let's check whether any other number is common in both these. Here there is no other common factors, so we will take HCF is equal to 2. Now coming to the LCM, we will be getting all the prime factors other than the common numbers, and whichever is common in both these numbers, we will take it only once. So you see, for these both, we will take 1, 2 here, and we are taking 2 into 3 into 5 into 17 into 23. In proper ascending order we have taken. Now we will take the product of this so that we can get the LCM of 92 and 510 as 23,460. Till this we have completed the first part of the problem. Now coming to the second and verification part, we will take HCF of 92, 510 into LCM of 92, 510, that is 2 into 23,460. We will get as 46,920. Now let us check it for the right hand side of the condition, that is product of the numbers. The original numbers are 92 and 510. While multiplying we get 46,920, and we can directly see that these two numbers are equal, but still we will put it in the proper condition form. HCF of the numbers 92 and 510 into LCM of 92 and 510 is equal to 46,920, which is equal to the product of the numbers. And this is what the condition we are asked to verify in this question. So till this, the second subdivision is over. Now let's solve the third subdivision, in which the numbers are given 336 and 54. First we will find the prime factorization of this numbers. So while taking 336, it is an even number. Whenever we get an even number, we will start the prime factorization with 2. So 2 into 168, 336, again an even number. So 2 into 84, 168. So again 84 is also even number. We will repeat this process. 2 into 42, 84, and 2 into 21, 42. Coming to 21, it is 3 into 7. So 3 into 7, 21. 7 into 1, 7. This is the prime factorization of 336. So we write 336 as 2 into 2 into 2 into 2 into 3 into 7. Now coming to the 54, it is an even number. So 2 into 27, 54. 3 into 9, 27, and 3 into 3, 9. 3 is a prime number, so 3 into 1, 3. Now writing 54 as product of its primes. 2 into 3 into 3 into 3. Now to find the HCF, we will find which factors are common in these two prime factorizations. First factor 2 is common in both, and second factor here 3 is also common in both these prime factorizations. So these two numbers we will take once for finding the HCF. So HCF is equal to 2 into 3 equal to 6. Now coming to the LCM part, whichever is common in both of these things, we will take those numbers only once, and all other numbers we will take as it is. So for these two 2, we will take 1 here, and for these two 3's, we will take 1 3 here. Otherwise, if we see, there are 3 numbers and 2 factors. So 2 into 2 into 2, and we are having here 3 into 3. There is one 7 also, so that also we are taking it for finding LCM. When we get the product, the answer is 3024, which is LCM of these two numbers. Now coming to the second part of the question, in which we will find the product of HCF and LCM as the left hand side. So we are finding it and we get it as 18,144, which is the product of 6 and 3024. Now coming to the right hand side of the condition, which we have to verify, we take the product of the given numbers. 54 into 336, which we get as 18,144. So we can clearly see that these two numbers are same and equal. So HCF into LCM is equal to the product of the numbers. That is 18,144, which we give here in this step in the proper format. Thus, we verify the given and required condition. Now, here the second question gets end, and now let us solve the third question. The third question reads that find the HCF and LCM of the numbers using prime factorization method. So the first subdivision, the numbers given are 12, 15 and 21. Here 3 numbers are given. So the previous condition which we were using, like LCM into HCF is equal to product of the numbers, is not valid here, because that is valid only when 2 numbers are considered. Here we are considering 3 numbers. So in this question we are going to find only HCF and LCM. Now let's find the prime factors of the given numbers. Like 12 is the even number, so 2 into 6, 12. Again it's an even, so 2 into 3, 6, and 3 into 1, 3. Coming to 51, it is directly 3 into 5. 3 and 5 both are primes. So thus ends the prime factorization of 15. Again 21 is 3 into 7, 21, 7 into 1, 7. Now let's list out the prime numbers. 12 is equal to 2 into 2 into 3, 15 equal to 3 into 5 and 21 equal to 3 into 7. Now let's find which are all the factors common in all the three given numbers. 2 is not common, 2 is not present in 15 or 21. Now coming to 3, yes, it is present in all the three numbers. So it is a common factor present in all the three. So for HCF, we will take it only once. All other procedures are same as we did for two numbers. We are going to do it for three numbers also. Only change is that the particular condition which we were using will not be valid here. So HCF is equal to 3, and for LCM, whichever the factor is common, we will take it only once, and all other factors will remain as it is. Like 2 into 2 into 5 into 7. We are taking it here also. 2 into 2 into 5 into 7. Thus, we get the LCM 420. Now, let's consider the second subdivision where the numbers given are 17, 23 and 29, where all three are prime numbers. Generally, we know that prime numbers are divisible only by 1 and itself. So, here the prime factorizations are directly 17 is equal to 17 into 1, 23 is equal to 23 into 1, 29 is equal to 29 into 1. But in general case, when we write the prime factors for a composite number, we don't mention 1 because we will be multiplying 1 in HCF. Again, the number will remain same because 1 is a multiplicative identity. But in case of prime numbers, HCF will always be 1 because that will be the only common factor between different prime numbers. Now comes the LCM. LCM will be directly the product of the given prime numbers, like 17 into 23 into 29, which is now let's solve the third subdivision of this question where the numbers are given like 8, 9 and 25. Now let's prime factorize it. 8 will be 2 into 4, 8 and 4 will be 2 into 2, 4. So 8 is equal to 2 into 2 into 2. Now for 9 it is directly 3 into 3 and for 25 it is 5 into 5. Now we will list out the prime numbers here, like 8 is equal to 2 into 2 into 2, 9 is equal to 3 into 3 and 25 is 5 into 5. Now here if we notice, though these three are not prime numbers, but still there are no common prime factors between these three. Then we will add into 1 in all the three prime factorizations. Thus we will get the HCF as 1 and LCM will directly be the product of the given numbers, like 2 into 2 into 2, 8, 3 into 3 will be 9 and 5 into 5 will be 25, and the product of which we get as 1800. Now let's move on to the fourth question. In fourth question, it is given that HCF of 306 and 657 is equal to 9 and it is given find LCM of the 306 and 657. So for any question of this type, finding the condition or the formula to apply and find is very important. So here what data is given, we will first collect it down. Like here, A is given. We know that HCF of A comma B into LCM of A comma B is equal to A into B. So this is the only condition we know here in this chapter related to HCF, LCM and the given numbers. So let's collect like A is equal to 306, B is equal to 357 and HCF is equal to 9. HCF of these given numbers is equal to 9 and we are asked to find the LCM. Now we are substituting these values in the given or the known condition. So for HCF we will substitute 9 LCM we have to find, so we'll write it as it is, like 9 into LCM of 306, 657, which is equal to the product of the given numbers. Now we will take the 9 that side. Here it is in the multiplication, so when it goes to the other side of the equal to sign, it will come in the division part. It will come as denominator. Now we can, 306 is divisible by 9, so we can cancel it like 9 3s are 27, 30 minus 27 will be 3, so 9 4s are 36. So it will be equal to 34 into 657, and we get it like 22,338 as the LCM of the given numbers. And this is what we have to find in this question, and we have found. Now let's move on to the fifth question. The fifth question reads that check whether 6 power n can end with the digit 0 for any natural number n. So in 6 power n, they are asking like if n is any natural number, can 6 power n end with digit 0? So now let's first understand what does it mean that if a number ends with the digit 0. Any number, let's take like 20, 30, 1080, any number ending with the digit 0 will be divisible by 10. For any number to be divisible by 10, the number should have the factors 2 and 5. Both should be present for the number to end with the digit 0. But here if we take, the number is 6 power n. 6 is an even number. So anyways it will be divisible by the prime factor 2. So here we should check whether it is divisible by 5 or not. Whether it has a prime factor 5 in its prime factorization or not. So that is what we are taking in the first step. Like 6 power n will end with the digit 0 if the prime factorization of the 6 power n contains 5 as a prime factor. But this is not possible, as we know that the prime factorization of 6 is 2 into 3, and we also know from the fundamental theorem of arithmetic that this factorization is unique. So there is no 5 here in the prime factorization of 6. So 6 power n cannot end with the digit 0. This is the conclusion we are arriving. Now coming to the sixth question, here it is asked that explain why the given two numbers are composite. First, let's see what composite numbers are. Composite numbers are those which can be expressed as product of the primes. Now, let's consider the given numbers one by one. First, we will consider 7 into 11 into 13 plus 13. Here in between there is a addition sign, plus sign. So, this is a number in the left side of the plus sign and 13 is right side to this. In these two numbers, 13 is a common number. In these two, 13 is common. So, using distributive property, we will take 13 as a common out and remaining numbers inside the brackets. Like 13 into 7 into 11 will be the first number, and 13 into 1, 13. Now let's simplify. 13 into 77 plus 1, and it will be 13 into 78. Now 13 is a prime number, so we will prime factorize only for the 78. 78 is an even number, so 2 into 39, 78, and 3 into 13, 39. We will write 78 as product of the primes, 2 into 3 into 13. In proper ascending order, if we give the solution, it will be like 2 into 3 into 13 into 13, which is equal to the given number 7 into 11 into 13 plus 13. Thus, This number can be expressed as product of primes. So this is a composite number. Now coming to the second part. The given number is 7 into 6 into 5 into 4 into 3 into 2 into 1, which is a single number, plus 5. In these two, 5 is common. So we will take it out of the bracket and inside it will be 7 into 6 into 4 into 3 into 2 plus 1. Now let's simplify. It will be 5 into 1008 plus 1 and it will be 5 into 1009. And 1009 is a prime number. 1009 is a prime number. So the given number is expressed as 5 into 1009, that is product of primes. So both these numbers are composite. Thus we have given the explanation for why these numbers are composite. Now let's see the seventh question. The seventh question is a little kind of application of this HCF and LCM topics. So let's see what the question is. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. So both Sonia and Ravi are going around a circular path which is constructed around a sports field. In that, Sonia takes 18 minutes to complete one round and Ravi takes 12 minutes to complete the same one round. Let's see ahead. Suppose they both start at the same point at the same time and go in the same direction. After how many minutes will they meet again at the starting point? So when Sonia and Ravi go around the circular path, then they may be meeting multiple times also, but we are calculating the time taken for them to meet at the first time. So that is why we have taken like minimum time for Sonia and Ravi to meet at the starting point. Whenever we take minimum time, we will use LCM, the lowest common multiple, and here the factors or the things under considerations are time taken by Sonia and time taken by Ravi. So we take LCM of 18 minutes, that is time taken by Sonia, and 12 minutes, that is time taken by Ravi. So we are finding LCM for 12 and 18, for which first we should find the prime factorization. 18 we will get 2 into 9 18 and 3 into 3 9. So prime factors of 18 would be 2 into 3 into 3. And again for 12 it will be like 2 into 6 12 and 2 into 3 6. So prime factors of 12 would be 2 into 2 into 3. For finding the LCM, first let us find which are all the common prime factors in these two. First 2, it is common in both of them, and next 2 there is no other 2 in 18. Coming to 3, it is also common in both of them. So we will take, for these two we will take 1 2 here, and for these two we will take 1 3 here. Other two factors we will take as it is, 2 into 3. So the LCM of 12 and 18 would be 2 into 2 into 3 into 3, which is 36. Here the required unit is in time. So we will take it in minutes, that is they will meet after 36 minutes at the starting point. With this question, we are completing exercise 1.1 of this chapter. So whatever theory part we have discussed in the beginning, I will post it in all 3 Instagram, Facebook and Twitter. You can take it from there, whichever will be convenient for you. For that, do follow me in these accounts in the name Dharani Murali. If you are new to this channel, do subscribe this so that you don't miss any video updates. In next video, we will discuss exercise 1.2 of this chapter. Till then, bye bye.